let's use our trick for solving systems of linear equations to attack this equation. So let's use elimination just because that's the one I like the most. And actually there's one more trick for elimination that can come in handy, which is there's one extra move you can make, which is you can interchange equations if you want. So I'm going to start out just by switching these first two equations. Because I like to have just, if I can get it, I like to have just x in my upper left-hand corner. That makes some of the rest of it a little easier. So x minus 4y minus z equals minus 4. And now I can add 2 times this to that equation. So 2 times x minus 2x, that's no x's. So right, the x term here is missing. And then 2 times minus 4y plus 8y, that actually eliminates the y's as well. And then 2 times negative z plus z, that's minus z. Okay, and then 2 times minus 4 plus 7, that's minus 1. All right, and now I can also use this x, I can add this equation to the last equation to eliminate this x down here. So that x plus x is no x, so there's no x's. And then minus 4y plus 4y, there's no y's either. And then minus z plus 3z, that's plus 2z. Okay, and then minus 4 plus 6, that's 2. Okay. So next thing we need to do is use this z here to eliminate the z's below it. So now we can add twice the second equation to the third equation. So we get x minus 4y minus z equals minus 4, minus z equals minus 1. And when we add 2 times the second, add 2 times the second equation to the third equation, we get 0 equals 0. Okay, and then as a final touch, let's multiply this second equation by minus 1 just to make these minuses pluses. All right, so at this point, we have this stair-step pattern, but something sort of strange has happened. First of all, there's no step in this stair-step for y's, and also there's this equation that says 0 equals 0. Now the thing about the equation 0 equals 0 is it doesn't tell you very much, right? We're looking for values of x, y, and z to satisfy these equations, but it's very, very easy to satisfy the equation 0 equals 0. You don't have to do anything. You don't have to be careful about how you pick x, y, and z to satisfy the equation 0 equals 0. So this equation 0 equals 0 isn't giving us any information, so we can just ignore it, right? It's automatically satisfied, so we don't have to worry about doing anything careful with x, y, and z to satisfy this equation. All right. Now we can back substitute. So we know that z is 1. We can put that into the first equation. We get x minus 4y minus z, which is 1, equals minus 4. And when we simplify this equation, we get x minus 4y equals negative 3. And so now we're left with these two equations. X minus 4y equals negative 3. And z equals 1. Right? Now, you can see that this system of equations isn't actually locking down a single value for x or for y. It does lock down a value for z, but there are many different possibilities for x and y. One way to express all of the collection of solutions here would be to solve this first equation for x. We would get x is 4y minus 3. Okay. Now our x, y, and z are, well, z has to be 1. X has to be 4y minus 3. And y, well, y can be anything. So what we can do is just leave it as y, right? So this is sort of shorthand for saying that y can be anything. But whatever you chose for y, x has to be 4 times that minus 3. Okay, so we get this collection of points where y can be anything. if we actually plotted all of these points in XYZ space, it turns out that this would give us a line. So the collection of solutions to this equation is actually a whole line in 3D space. The reason why this happens is because so we had three equations. Now, if you think about an equation with just x and y, that gives you, right, if you have a linear equation with x and y, that gives you a line in 2 space, like this. Okay, well, it turns out an equation in x, y, and a linear equation in x, y, and z gives you a plane in 3 space, like this. We had 3 equations, so we had 3 planes, and what happened is, so here's our second plane. You can see that 2 planes intersect along a line. Well, we had 3 planes, so it turns out that we had 3 different planes that all intersected along a line, like this, right? It's as if these planes were pages in an open book, and the pages all intersect along the spine of the book. In general, if you have 3 planes sitting in 3 space, you'll have, so one plane like that, one plane like this, and then maybe a third plane like, oh, my picture is getting pretty messy here. How do I want to draw my third plane? Maybe my third plane could be coming down like this. Okay, so in general, if you have 3 planes sitting in 3 space, they'll intersect. Oh, I've done a bad job of drawing the general situation. Let me start over. So let's see. Here's one plane. Here's another plane. And then the third plane I'm going to draw like this. Okay. Now the first and the second planes intersect along this red line here. The second and the third planes intersect along this blue line. And the first and the third planes intersect along this green line. And you can see that all 3 of these lines intersect at this single point right here. So usually when you have 3 equations in 3 variables, that gives you 3 planes, and usually those 3 planes will intersect in just a point. So what's funny about this system of equations is because we didn't get that full stair-step pattern, they actually intersected in a line like this. So it's actually special for planes to intersect along a line. Usually that doesn't happen. All right, let's look at one more system of equations. Let's try this one. So we can play the same game with trying to add multiples of equations to other equations to try to zero things out. Oops, I meant for this to be a y right here. Okay, so let's start out by subtracting the first equation from the third equation. So the first equation we're going to leave alone. It's x plus 3y minus 3z equals negative 2. Second equation we're leaving alone, so it's y minus 2z equals minus 1. And then third equation is, so now remember we're subtracting the first equation from the third equation, so no x's, and then minus y plus 2z equals 2. Yes. Yes. Okay. Now we need to use this y right here to zero out the y below it. So we're going to add the first equation to the third equation. Now that doesn't change the first 2 equations. So x plus 3y minus 3z equals minus 2. Second equation is y minus 2z equals minus 1. And then the third equation, let's see, it looks like our y's cancel. Our z's also cancel. And then on the right-hand side, we get 1. Okay, so at this point, we've done all of the elimination that we need to do to get this stair-step pattern to our variables. But now we're left with this equation that's 0 equals 1. Well, remember, our goal here is to find values for x, y, and z that make all of these equations true. But this equation, 0 equals 1, this is never true. it's impossible to pick x, y, and z to satisfy this equation. This equation is always false. So that means this system of equations has no solutions. So system has no solutions. So what's happening here geometrically is these three planes, it turns out that two of them do intersect. So one plane might be like that, and the second plane might be like this. So the first two planes do intersect along a line, but the third plane is actually parallel to one of the first two. So these three planes never all intersect together, right? They intersect pairwise, but they never all intersect each other at the same point. And that means there's no single point that lies on all three planes, and that means that there's no solution to this system of equations.